Hello, in this video I would like to discuss Graham's law of effusion and also how it relates to the kinetic molecular theory of gases as we discussed in class. And just to recap, the rate of effusion is inversely proportional to the molar mass of a gas. So as the molar mass of a gas becomes smaller, the rate of effusion increases because these molecules move faster. And we can use that property to evaluate rates of effusions of two different gases and with each other. So if we compare the rate of effusion of one gas and the other one, it will correspond with the molar masses or atomic masses of each gas. Now we can rearrange this equation right here and use that in, say, in an instrumental analysis to determine, like an unknown gas, if we realize the rate that we're talking about here in this equation right here is the amount of gas over time that is effusing out of the little pinhole or little orifice that we have in a cup. So if the same amount of gas over time is going out, then we can standardize that. So we can rearrange this equation right here and list the amount of gas over time that is effusing out of the hole, and this for A and B. So amount of the number of moles of A over the time it takes for these number of moles of A to emerge from that little hole, and the amount of B for over the time that amount of moles of B need to emerge from that little hole or that little pore. It'll also relate to the molar mass of those two. Now we can then make an assumption, say, do an experiment where we keep the amounts of A, the number of moles of A and B the same, and find out an unknown gas. So for example, then we can cancel this out, and so if the amount of A is equal to the amount of B, then all we need to worry about is the time that these two need to effuse right here. So the way we can set this up is then via a device like this, where we have like an open tube where we can inject some kind of gas into that tube and have a detector on the other end. So here we then have some gas that we inject here at the beginning of the tube, and if we always inject the same amount, then we just start a stopwatch, and then we have a detector at the end that goes beep, and we can then find out, depending on the time that it took for this gas to travel down this tube, we can then determine what the gas type might be. Now, for most gases, they travel so fast that we could not really measure this reliably, so we can, for example, pack this column with sand or baking soda or something to make the path that the gas needs to take a little bit more longer, and we can then inject a standard gas and an unknown and then determine what the unknown gas is, for example. So if we, for example, use chlorine as a reference gas, so use chlorine gas as a reference, and let's say we do this experiment and find that the time for chlorine to come out is 0.885 minutes. And then we have an unknown gas that we're trying to investigate, and to find the molar mass of that one. And the unknown, let's say, is 1.16 minutes. So we can now make the assumption, okay, it's probably a heavier gas. And now, since we can use that relationship that we came up with earlier, since time is inversely proportional to the root mean square of velocity of the gas, we can then therefore make the assumption and calculate the molar mass right here. So we can again find our equation, time 1 over time 2 equals the square root of the molar mass of gas 1 over the square root of the molar mass of gas 2. And in this case, we can then rearrange this to make those two equal, so 0.885 minutes over 1.16 minutes. This is supposed to be in minutes. 1.16 minutes and that equals then the square root of the molecular or the molecular mass of chlorine, and that is 70.9. Remember, chlorine is Cl2, so it's not 35. So square root of 70.9 grams per mole. And then over the molar mass of the unknown. And now all we can do is cross multiply right here, so we can cross multiply and solve for the unknown. And so we end up then with 1.16 times 70.9 grams per mole divided by 8.55. So, and that equals then the mass of the unknown, and solve for that one. So we can then solve for the unknown, the square root of the mass of the unknown, or the molar mass of the unknown. And then we have 1.16 over minutes times the square root of 70.9 grams per mole over 0.885 minutes. And the minutes cancel out. And now we can solve this and rearrange this to find and so we basically divide this and then find that this 1.16 divided by, 1.16 multiplied by the square root of 70.9 divided by 0.885, and now these units right here, you need to bear with me here for a moment, so we will take the square root of these units, but then we will need to square this number, the molar mass of the unknown, to find the molar mass. So let's do that. So we end up with the square root of the mass of the molar mass of the unknown equals 11.4 over the square root of grams over the square root of grams over the square root of moles. And now all we have to do is square all this, so we can get rid of the square root terms right here. And we are, so let's do that, 11.4 and then we square that. So we end up with about 129.96, 130 grams per mole. And then if we can then go look in our periodic table and see what this may be, and then we see that xenon has an atomic mass of 131 grams per mole, so maybe if we repeat this experiment once or twice, we'll hone in on a closer value. So this is probably xenon is 131 grams per mole, so it's probably pretty close. Maybe we have xenon right here that we're dealing with. Here's another example. See if you can do this little quiz, and thanks for watching.